Science editor Steve Newman reports on one person already using the brand new system.
Hi everyone, good morning, good afternoon, or good evening whenever you're watching this video. In this video I'm going to be talking about the properties of water. In the previous chapter I went over covalent bonds and hydrogen bonds and some properties of atoms. So if you didn't watch that video or you're not familiar with covalent bonds or hydrogen bonds, I would highly recommend watching that one before you watch this one. So we're gonna get right in now and talk about the properties of water. Let me just go ahead and minimize my screen and get my PowerPoint going. So again, we're going to be talking about the properties of water today. Let's first take a look at the structure of water, right? H2O. I mean, you have probably heard about H2O, water, ever since you were a kid, right? So you've got the H2O, two hydrogens, and that's what these two atoms represent. You've got the two hydrogens, and then over here in the middle you have the oxygen. Okay, the thing about oxygen, remember in the previous video we said that it is extremely electronegative. More on that in a couple minutes. But oxygen has an atomic number of 8, so it has 8 protons and 8 electrons. Okay, so it's got 2 electrons in the first energy level, and then it has 6 electrons in the outermost energy level. Okay, so I'm just going to draw them as pairs. Here's my first 2 pairs and on the second energy level, and then it's going to have 1 electron here and 1 electron here, and it needs 2 more electrons to become stable, right? So oxygen is an unstable element by itself, and so it's going to, in this case, share electrons with 2 hydrogen atoms. So remember, a hydrogen atom is pretty small. It only has 1 electron and then 1 proton. And here's another hydrogen atom, 1 electron and 1 proton in the middle. I'll just write 1p to represent the 1 protons each. Okay, and then in here we have the 8 protons. Okay, so these 2 hydrogen atoms are going to come in and they're going to share. So I'm going to redraw them. There's the electron from hydrogen. Ooh, all these circles are kind of blending in with each other. So let me just go ahead and color in all the electrons so it's less confusing. Okay, so now if we count all the electrons on the valence shell for oxygen, it has 8 electrons, right? 1, 2, 3, 4, 5, 6, 7, 8. So now it's stable. So this is H2O. You have 2 hydrogens covalently bonded with this oxygen atom by sharing electrons. Okay, so that is just the basic structure of water. And again, when we say a covalent bond, which is sharing electrons, this is not just any ordinary covalent bond, right? It's a polar covalent bond, polar. And when polar covalent bonds are formed, it makes a polar molecule. Okay, it makes a polar molecule. Remember, polar molecules have charges on them. Okay, and so because oxygen is electronegative, it shares the electrons unequally with these 2 hydrogen atoms. As a result, the electrons are spending way more time with the oxygen atom end, leaving the hydrogens with a partial positive charge and then a partial negative charge by the oxygen, because the electrons are negatively charged. And if the electrons are negatively charged and they're hanging out with the oxygen more than the hydrogens, then there's going to be a negative charge. Okay, so water's a polar molecule because there's 2 poles in this case. You have a positive pole on this end, okay, and then you have a negative pole up here where the oxygen is found. So when we say oxygen is electronegative, I kind of went over this in the previous video, like what does that exactly mean? You know, the oxygen atom, it pulls the shared electrons towards it. Why is that? Well, because at the center of the oxygen atom, there are 8 positive protons. So there's 8 particles that are positively charged pulling on the negatively charged electrons. Remember, opposite charges attract. Because there's 8 of them compared to the hydrogens. Hydrogens only have 1 proton. So that's only 1 particle with the positive charge, whereas in the middle of the oxygen, there's 8, okay? There's 8, so there's a stronger pull. And it also has to do with the size of the oxygen atom. The oxygen atom is pretty small, okay? And so the electrons are kind of close to the nucleus, and so the pull is really strong. That's what we really mean by electronegativity, okay? So oxygen is a very electronegative element. And as a result, and I apologize, this picture isn't the greatest, it's very pixelated. As a result, the electrons tend to spend more time by the oxygen. And so you can see in this diagram that, the density of electrons it's much more dense. It's higher density over by the oxygen atom than the hydrogen atoms, okay? And so this is from a POGL worksheet. It's showing you that the density, electron presence, the density of electrons is much more dense over by the oxygen than by the hydrogen. So again, electrons are negatively charged, right? So there's a higher, there's going to be a negative charge over here, leaving the hydrogens positively charged because electrons are moving in this direction, being pulled towards the oxygen. So that's why water is a polar molecule. And you guys, this video and in this chapter, we're going to be talking about the properties of water and the properties, the behaviors of water. It comes down to the fact that water is polar. Okay, so everything that we're going to be talking about in this video about the properties of water, it really goes back to the fact that water is polar. Water has a negative N and a positive N. And that is due to the fact that oxygen is electronegative. Okay? Oh, let me go ahead and mute that. Sorry about that, everybody. So in a beaker or a cup of water, you have water molecules. They're all polar, right? You've got the positively charged hydrogens and negatively charged oxygen. They're going to be attracted to other water molecules because other water molecules are also polar with opposite charges. So this, the dotted line that you see here and here and here and here, those are all hydrogen bonds, okay? They're called hydrogen bonds because the positive hydrogen is attracted to a negatively charged atom or molecule. And in this case, it's negatively charged oxygen of another water molecule, okay? So don't get confused about like hydrogen bonding. A lot of students think that hydrogen bonding is like within the water molecule for some reason. They think that it's the hydrogens bonded to the oxygen. No, hydrogen bond is the positive hydrogen attracted to a different molecule that is negatively charged, a separate molecule that's negatively charged. So like this is a hydrogen bond, okay? Whereas the hydrogen covalently bonded to the oxygen, that's a different kind of bond. So in any cup of water, you're going to have water molecules attracted to each other, okay? And you see that like drops of water will tend to like on like a window. Like let's say that you're sitting in the car and you're looking out the window and it's raining outside. You'll see raindrops, like they'll congregate together. They'll like come together. They'll merge together because water is attracted to water because water, again, is a polar molecule. So that's why water is attracted to water, and that's what we call cohesion. Hydrogen bonding between water molecules is responsible for cohesion. Cohesion is when molecules of the same kind are attracted to each other. Water attracted to water. When like substances are attracted to each other. Okay? So in this diagram here, in the water droplet down here, okay, you have all these water molecules that are surrounding each other and they're all attracted to each other. That's cohesion. And then at the surface, you have water molecules that are attracted to each other. But because, like, let's say we're focusing on this water molecule. because this water molecule is not surrounded by other water molecules, the cohesive forces between the water molecules at the surface is stronger. The hydrogen bonding is actually stronger than if it was a water molecule that was surrounded by other water molecules. And that's what we call surface tension, okay? So water has a lot of surface tension. Water attracted to water at the surface is responsible for surface tension, and the hydrogen bonding at the surface is stronger than the hydrogen bonding that occurs within the water droplet, okay? And you can see here that a spider, and in this case this is a water strider, and a leaf, they can actually float on top of the surface tension without breaking the hydrogen bonds, okay? So there's like, I know that there is a lizard, the basilisk lizard or the Jesus lizard, that can like use the surface tension on water to, it can run across the surface of water. It can run across the surface of water. It can use the surface tension without breaking the hydrogen bonding. It can go from one side of the river to the other side of the river, or the other side of the lake to the other side of the lake. The water striders and spider can also like glide across the water because of the hydrogen bonding, okay? There's a great video on YouTube if you want to look it up. I think it's titled Astronauts Bringing Out Water from a Towel or something like that. It's yeah, I usually show that video to my kids. It's a really cool video. Hydrogen bonding between water molecules and other polar substances is responsible for adhesion, okay? So cohesion, remember, is water attracted to water, like substances attracted to each other, whereas adhesion is hydrogen bonding between water and other polar substances, okay? So in this photo, okay, you have water droplets that are sticking to a spider web. Spider webs are made out of protein, and protein is polar. Protein, the amino acids that make up protein, they have positive charges and negative charges. So that's why water sticks to the spider web, okay? And then this is what we call this curvature when water is in a narrow tube, glass tube. When water is in a narrow glass tube, it will not be straight at the surface, but it's curved, and that's called a meniscus, because the water is attracted to glass. Glass is also polar, okay? Glass is also polar, and so water is going to be attracted to it, and that's called adhesion. So cohesion and adhesion work together in capillary action. So capillary action is actually, it's very important for plants, because when plants absorb water at the roots, the water is going to move up through the root system, through the trunk of the trees, through the branches, and then water is eventually going to evaporate out through the leaves, okay? And water is going to end up in the air, okay? And some of that water that ends up in the air can form droplets and come back down, okay? And other times that water can evaporate and go into the atmosphere and form clouds, okay? But capillary action is how water goes from the roots all the way up against the pull of gravity and then out through the leaves of plants, okay? So capillary action is cohesion and adhesion working together. Cohesion, and you can see that I should go back and describe what's going on in this picture, but when you take a cross section, like if you were to, well, hopefully you don't cut down this tree, but if you were to take a peek, okay, into the trunk of a tree, you'll see that there are long vertical microscopic tubes. There are these little tubes that run through the entire trunk, and those tubes are called xylem tubes, okay? The xylem tubes are made out of xylem cells, and so this is a xylem tube right here, okay, in this picture. And so by cohesion, water is attracted to water as water moves up they pull each other up because water is attracted to water, like magnets are like pulling each other up. Whereas the xylem cells are made out of cellulose. Okay, cellulose is a type of polysaccharide, a long chain sugar. And so polysaccharides and sugars, they're polar as well. Okay, they're polar as well. So the water is attracted to the xylem cells, the xylem cell wall, the plant cell wall, the cellulose. Okay, so you can see here the cell wall of this plant is also polar, and so they're going to form a hydrogen bond. Water's going to form a hydrogen bond with the cell wall. So that's how like water is attracted to the capillary tubes or the xylem tubes, the xylem cells. And so by cohesion and adhesion together, water is going to move up through the plant and then out through the leaves. Okay. So, you know, the water that's coming in is going to be used for photosynthesis. It's going to be used to transport food, okay, and minerals. But majority of the water will be evaporated in a process called transpiration. Okay, we might talk about that later on this year. But transpiration is a process by which plants will like move and evaporate water through the leaves. And that's plants are able to do that by capillary action. All right, so that's that. And then another property of water besides cohesive and adhesive property of water is that water is a really good solvent. Water is a really good solvent. And the reason why it's a good solvent is because water is polar, right? Remember how I said just a few minutes ago that all the properties I'm going to be talking about in this video it goes back down to the fact that water is polar. Okay, so water is a good solvent. What is a solvent? A solvent is a substance that can dissolve other substances. Okay, so there's a lot of things that you can mix in water that dissolve in water. Like you could take some honey, dissolve it in water. You could take some sugar, dissolve it in water. You could take some salt, dissolve it in water. And we'll use the example of salt. Okay, here is a salt crystal. Salt is made out of a sodium ion, a negative sodium ion, and positive sodium ion and a negative chlorine ion. And excuse me, let me just have a drink of water. And this molecule of salt, so this molecule of salt is due to an ionic bond. What happened is that sodium is unstable. Chlorine is unstable. Sodium has a valence of 1. Chlorine has a valence of 7. Sodium wants to get rid of that electron. So that electron will go to chlorine. And when sodium loses that one electron, it becomes a positively charged ion. And when chlorine gains that negatively charged electron, it gains a negative charge. And so now you have like two ions. I should have circled them separately. So you have a positively charged ion and a negatively charged ion, and opposite charges attract. So salt, you know, the type of salt that you add to your food is NaCl. It's an ionic substance. We say that it's an ionic substance because it's made through hydrogen bonding, okay? And it is a weak bond, as we said in the previous video, in the previous lesson. The ionic bonds are pretty weak because if a positive charge comes along, it can take that negative chlorine away. If a negative charge particle comes along, it can take that sodium, positive sodium away, okay? So it's like a bond of attraction. I mean, it's sort of like, that can kind of relate to even relationships, right? If a relationship is based on attraction, and attraction alone, is it going to last? No, it's not going to last. Okay, so water is polar, and it can actually pull apart sodium and chlorine ions. Okay, sodium and chlorine ions. It can pull apart the salt molecule. Okay, so in this diagram, you can see here that the sodium is yellow, and it's got the positive charges. The chlorine ions are blue. It has a negative charge. And so when salt dissolves, how is it dissolving? Well, the water molecules will surround each ion and pull them away okay? So we call that a hydration shell when water molecules surround the ion. And notice how in the negatively charged chlorine ion, what part of the water molecules are facing it? What part of the water molecules are facing the negatively charged chlorine ion? It's the positive hydrogens. See that? Okay. So the positive hydrogens are facing the negatively charged chlorine ions. And so they form a shell. They form a shell. They surround it, separating the negatively charged chlorine ion from the positively charged sodium ion. And notice what's surrounding the sodium ion? It's the negatively charged oxygens. They're the ones that are attracted to the positively charged sodium ion. Okay, so eventually what's going to happen to this salt crystal is that it's going to be completely dissolved. Each ion is going to be surrounded by water molecules, and that's how it dissolves. That's why we say water is a good solvent, because water can take apart all of the ions that make up the salt crystal. Okay, I hope that makes sense. So what type of substances dissolve in water? Like we said, ionic substances, right? Polar substances, or anything hydrophilic, okay? Hydrophilic means water-loving, and so water-loving substances are polar substances, ionic substances, okay? So I guess you can say that the word hydrophilic is kind of a general term, and that polar and ionic substances, they are hydrophilic, okay? They have polar molecules have charges on them, ionic molecules or ions, okay, or molecules, ionic molecules or ions, they have charges and they're hydrophilic, so they can mix with water. And when they mix with water, they could be dissolved in water. Okay. So what type of substances do not dissolve in water? That would be hydrophobic, right? Or non-polar substances. Hydrophobic means water-fearing. Non-polar means there's no polarity, meaning there's no charge. There's no positive or negative charges on the overall molecule. An example of that would be like oil. When you have oil and water together, they're going to stay separate as separate substances because one is hydrophobic, one is hydrophilic, or one's water. And so the hydrophobic oil is not going to want to mix, okay? So oil, fats, okay, like the fats in butter are also hydrophobic. Let me show you a picture of what a fat molecule looks like. Okay, so this is a fat molecule. A fat molecule is made up of really four things, okay? This is the glycerol molecule, and then it's made up of 1, 2, 3, okay, 1, 2, 3, fatty acid chains. Fatty acid chains. The fatty acid chains are what we call hydrocarbon chains. And why do you think it's called a hydrocarbon chain? Because see all the hydrogens and carbons? It's just made up of a ton of hydrogens and carbons. And carbon and hydrogen, they are not electronegative. They're not electronegative. So like methane, remember methane, CH4? When carbon shares, CH4. When carbon shares electrons with 4 hydrogens, it's shared equally. And when electrons are shared equally, you have a non-polar covalent bonds. Okay, so fat is a non-polar molecule because there's a lot of hydrocarbons in there, and hydrocarbons are made from non-polar covalent bonds because carbon and hydrogen are not electronegative. So hydrophobic substances, they're not attracted to H2O and they're non-polar, okay, because of the hydrocarbons. Some of you may have noticed here that there are a couple of oxygens in the fatty acid chain and the glycerol, okay? So yes, oxygen is electronegative. Yes, there is a slight negative charge on these oxygens, but guess what? Fat is such a big molecule that those oxygens that have a negative charge is negligible. And so the overall fat molecule, or triglyceride, okay, the overall fat molecule is nonpolar because those hydrocarbons are so long, the chains are so long, that we say that fat is nonpolar, okay? And this is just a cartoon that I found online that I thought was really cute. So we've got a polar bear down here, and then we have a grizzly bear, and the polar bear is saying, "Help, help, I'm dissolving." And then the grizzly bear is saying, "But bears are insoluble." And then the polar bear says, "That's easy for you to say, you're not polar." Get it? Because a polar bear is polar and it can dissolve in water. Okay. Anyway, I just thought that was a really cute cartoon. Okay. Next, the next property of water is that ice is less dense in solid form. So water, when it's a solid, it's less dense than liquid. I like this diagram because it shows you visual of what I'm talking about. Liquid water, liquid form of water, the water molecules are, they're moving around. Remember when you were like in middle school or elementary, you talked about like the 3 states of matter. You've got this solid, liquid, gas, right? And do you guys remember like which state of matter has the most movement? It should be gas, right? Gas molecules are moving around really, really quickly. And then liquids are moving around pretty quickly as well. The molecules are moving around each other. And then in a solid substance, they're kind of just vibrating, but they're not moving around too much, right? So with liquid water, the water molecules are moving around each other. They form bonds. Okay, so you can see here that they form hydrogen bonds. But as they move past each other, then those bonds break. So the thing about liquid water is that the hydrogen bonds are being made and broken, made and broken, made and broken, like constantly, okay? Whereas so that's why up here it says loose hydrogen bonds between water molecules. Whereas in a solid form, the water molecules are not moving around that much, and so they're kind of slowly moving, but when they do form a hydrogen bond, it's pretty stable. It's a pretty stable hydrogen bond. As a result, they form this crystal pattern, okay? Because each water molecule can form 3 to 4 hydrogen bonds. In this picture, you can just see that they form 3 because you're just looking at one plane. But if there was another set of water molecules in front, like this hydrogen atom would be bonding with another oxygen. And so this water molecule actually can form 4 bonds, okay? But anyways, as I was saying, so it forms this crystallized pattern. And notice the gap. Do you guys see these gaps in between, the space in between the water molecules? So water is less dense. It's less dense. There's a lot of space in between the water molecules. As a result, solid water or ice, what we call ice, floats on liquid water, okay? So because it's less dense, it floats. And this is actually really important because we talk about aquatic habitats. So habitats with water, when it gets super cold in the wintertime, a layer of ice forms. The ice floats at the top and it stays at the top, and it actually acts as an insulating barrier. So let me show you on the next slide. Okay, so the water, as the temperature outside is freezing, the water is going to freeze over and you're going to have the solid ice floating on the top, whereas the temperature down below stays warmer, so cold, okay, but warmer. And as a result, organisms, animals can live on the ice, like polar bears and penguins, okay? And then fish can swim. That's supposed to be a fish. That doesn't really look a fish, does it? Maybe this one's better. Okay, then the fish can live happily under the layer of ice in liquid water. If water did not float and it was heavy as a solid, let's say that the ice forms and then it just sinks to the bottom. So this is ice, it sinks to the bottom. Then eventually what's going to happen to the entire lake? It's going to freeze over and become a solid block of ice, right? And then how long would that take to melt, right? That would take forever to melt. Like glaciers, right? Glaciers have been around for a long, long, long time, right? And it's only in the last like 100 years that they're really, really starting to melt, or maybe thousands of years, it's really starting to melt. But anyways, ice, because it floats as a solid, it acts as an insulator. It acts as habitat, which is extremely important for ecosystems and animals that live in those type of polar habitats. Okay, I just found this meme online. I thought it was funny. Do you guys know who Ice Cube is? I hope you do, okay? He's like an actor and rapper, okay? His name is Ice Cube. No life vest needed because ice cubes float. Anyway, I bet you this picture is from a movie. All right, another property of water is that it resists temperature change. When you like boil water, it takes a bit for it to change temperature. When you compare that to other liquids like alcohol, alcohol changes temperature super quick, but compared to other liquids, water is pretty resistant to temperature change because a lot of the energy, the heat energy that it's absorbing from, like, let's say the stovetop, that energy is going to be used to break these hydrogen bonds. So when these hydrogen bonds are broken, they can also be remade. Okay, so a lot of the energy gets absorbed to break bonds, and then those bonds come back together. So we say that water has a very high specific heat capacity. You guys, that just means that water has a high capacity to absorb energy before it changes temperature. It absorbs a lot of energy before changing temperature, before changing state. Okay, and when I mean state, from liquid to gas. And so once the hydrogen bonds are broken, then it can turn into a gas. Okay, so water resists temperature change. It has a very high specific heat capacity. It can absorb a lot of heat energy before changing temperature when compared to other liquids. So how is water's high specific heat important for living things? Well, if you were an organism living in an aquatic environment like this fish, you wouldn't want your environment to be changing temperature so easily, and then eventually could evaporate, right? So water can absorb a larger amount of heat energy before its temperature increases by a significant amount, and that's important for aquatic ecosystems and habitats. And then also water, because of water's high specific heat, it keeps land near water. Land temperature is pretty moderate. Okay, so if you live like in Santa Monica by the beach, it's pretty cool down there compared to the valley, right, where we live. In the San Fernando Valley, it's like 100 degrees today. It's super hot. But if you were to go to the beach, it's like 75, 70 degrees. So that's like a 30-degree difference. And why is that? It's because of this nice cool ocean breeze coming in, because all of that heat energy can be absorbed by the Pacific Ocean, okay? And it takes a lot of energy for water to change temperature, okay? And then also all of that nice cool air comes into the land, and it cools the land, okay? So it moderates temperature on land. I mentioned this earlier, that it takes a lot of energy for water to evaporate, because water can absorb a lot of energy before it does evaporate. So we say that water has a high heat of vaporization. You guys, this is another property of water that's due to the fact that water is polar, right? Because water is polar, it forms hydrogen bonds. It's like forming bonds with each other, and they're like holding on to each other, and they're not evaporating from each other, okay? They're not like going away. Like this water molecule here is saying bye-bye to all of its water molecule friends, okay? They can absorb a lot of heat energy before they evaporate. And this is really important for living things as well. So in terms of biology, it's really important for habitats to be maintained. If you were a fish living in a lake, you don't want your habitat to evaporate, right? So you have a home for aquatic animals. And then for animals such as dogs and humans, we use a lot of evaporative cooling. Okay, it's called evaporative cooling, okay? So actually this picture, and this picture shows how animals use water to cool down, okay? In our sweat, our sweat contains mostly water, and as it absorbs that body heat from our skin, it's gonna absorb that heat, change into gas, evaporate, and go into the air. And when it goes into the air, it's absorbed that heat energy, and now that heat energy is within the water molecules and it's gone. Okay, so it helps cool you down. You know, you can feel that, right? You jump into the swimming pool, you go into the ocean, you come out, and then you just feel this the water evaporating off your skin, and it just feels so nice and cooling, right? With dogs, they're like panting because all that saliva in their mouth, it evaporates. And as the saliva, which is mostly water, evaporates, it helps cool their internal body temperature from the inside. And then you can see here, this elephant is just spraying its body down with water. The water is going to absorb the body heat, evaporate, and take that heat away and cool down, help cool down the animal. The last topic is ionization of water and pH. Water ionizes, okay? Remember what an ion is? An ion is an atom or molecule with a charge, okay? So I'm just gonna draw this really quick. So we've got our water molecule. This is the H2O, okay? I have another water molecule here. I'll draw it like this, okay? And remember, oxygen is very electronegative. It can pull, okay? It can actually pull this atom, the hydrogen atom, off of this water molecule. And so what you end up with is that and this, okay? So this is OH minus. It's an ion now. It went from H2O to OH minus. And then now over here, you have H3O plus. It has a positive charge, okay? Because of that positive proton in the hydrogen, okay? So when we say water ionizes, it can ionize into OH minus or H3O plus. And sometimes we don't, this is what we call a hydronium ion, and we can also just say an H plus, okay? So we could just refer to the H as H plus, okay? Because think of it this way, as the hydrogen atom, pops off, that's our H plus, okay? So when water ionizes, okay, let me erase everything first so we can kind of erase all, okay. So water, H plus splits off from H2O, leaving OH minus, okay? And water, in any cup of pure water, there's an equal amount of H plus ions and an equal concentration of OH ions. So these brackets mean concentration, okay? The amount of in a specific volume. Concentration is the amount of something, of a substance in a specific volume. So it's equal. And we say that water is neutral. Water has a neutral pH, okay? Oh, I forgot to say, pH stands for the power of hydrogen, and it's referring to the H plus. Power of hydrogen ions, okay? Because pH is a measurement. pH is a measurement of hydrogen ions. And in the case of neutral substances, the amount of hydrogen ions is the same. It's equal to the amount of OH ions. Whereas an acid has more H plus ions than OH. It has more, okay? So by definition, an acid has more H plus ions. And by definition, something that's basic has less H plus ions and more OH minus ions, okay? So the pH scale, it basically tells us how acidic or how basic a solution is based on how much H plus, based on the concentration of H plus. So the pH scale tells us how basic it is or how acidic it is. And so let me show you the scale. The scale is from 0 to 14. Something that's very acidic, right, has a high H plus concentration. It has a very high H plus concentration. So like hydrochloric acid is a very strong acid, okay? It has the highest H plus concentration. Whereas stomach acid is pretty strong as well. It has a pH of 2. It has 10 to the minus 2. Vinegar has 10 to the minus 3, therefore a pH of 3. So notice this, okay? So the pH is like the inverse log of the concentration, okay? So stomach acid has a pH of 2 because the concentration is 10 to the minus 2. Whereas pure water is neutral. Your blood is neutral. It has a pH of 7. It's neutral, meaning that the concentration of H plus is equal to the concentration of OH minus, okay? Something that's a very strong base would be like sodium hydroxide, oven cleaner, bleach, okay? Bleach is, I mean, if you've ever gotten bleach on your skin, it actually really stings and it hurts because anything too basic or acidic can be damaging, okay? So anyways, that is it for this presentation. I hope that it was helpful and that you learned something about water, the properties of water. Again, the properties of water it goes back to the fact that water is a polar molecule. And because the reason why water is polar is because oxygen is electronegative, okay? All right, I hope you guys have a good day and I will talk to you later. Bye.